Hi everyone, my name's Tim Comport and today I'm going to show you how I reverse engineered a classic MS-DOS video game. The game was released in 1995, it's on the list of 100 worthwhile DOS games, and it pioneered a number of technologies now used in almost all 3D games, but you likely haven't heard of it. The game is called BioForge and it was created by Origin Systems. I love playing video games, as you might have guessed. This is the earliest photo I could find of me playing games on an Apple II Plus clone when I was about 3. Over the years, I've spent a lot of time playing computer games, but I've also spent a lot of time trying to get computer games to run. And I'm not just talking about blowing into cartridges, although I've done my fair share of that as well. I'm talking about fiddling with jumpers on your Sound Blaster 16 so that you could get the sound working. I'm talking about running check disk and defrag to optimize your 500 megabyte hard drive. I'm talking about creating a game-specific floppy boot disk and crafting config sys and autoexec bat files to maximize the amount of available memory. And these are the actual steps that I did as a 12-year-old to get BioForge running. But rather than put me off, they made me more curious about how the game actually worked. So I dug around in the game files and I started piecing together interesting bits and pieces. Every couple of years, I would take another look and discover something new as I became a more knowledgeable developer. And that's how I now have an ongoing multi-decade hobby project. In 2006, I finally did release an app I imaginatively called BioForge Tools. It let you open and view pretty much all of the BioForge media, and I left it at that for many years. But recently I was looking for a fun project to mess around with .NET Core, and so I decided to write a cross-platform BioForge engine based on my previous work. But before I get into that, I just want to tell you a bit about how I got to this point. So the most important step when you're reverse engineering anything is to know your enemy. Even the smallest detail that you learn may save hours or weeks of effort. So let's start by learning a little bit about BioForge. So this is the award-winning box art of BioForge. I remember when I first saw the box thinking, if the game's anything like these artist impressions, it's going to be awesome. Only to find out later that these are the actual in-game screenshots. I wanted to show you the box, not just because it's cool, but also to highlight a couple of disclaimers. First of all, BioForge is covered by copyright, and the copyright belongs to Electronic Arts. I did speak with an IP lawyer in preparation for giving this talk, and so I'd like to say, in giving this talk, I'm not suggesting or encouraging you to infringe any copyright laws. What I do encourage, though, is that if you are or you plan to reverse engineer any software, be mindful of the legalities. And if you're unsure, either don't do it or talk to a lawyer first. Particularly with modern software, you have to worry about things like end user license agreements in addition to copyright. If you're interested in playing BioForge, it's still available to buy through Good Old Games at GOG.com. The second thing I'd like to point out is that BioForge is rated M17+. And at the end of my talk, I will be running a clip from the game that includes a stylized operating theater and some pixelated blood. The pixelation is not intentional, but the native resolution of the game is only 320 by 200. So if that's something that triggers you, not the resolution, the blood, I encourage you to look away for about 30 seconds when the time comes. I'll let you know when that is. So BioForge is an action-adventure game where you play a character that's been abducted to an isolated moon. He's had his memory wiped and has been surgically altered to become a cyborg assassin. And to progress through the game, you have to solve puzzles using items and explore the moon to find out who you really are. And you have to beat up some bad guys along the way. This is at the very start of the game, and if you don't immediately kill this robot, it puts you straight back to sleep. I remember reading reviews of people giving up before they even got started, not knowing what to do. There are logbooks and computer terminals throughout the game, which provide a very fleshed out background story and gives you information to help solve physical puzzles. Although BioForge had great reviews and was considered by many to be ahead of its time, it didn't sell very well. It's possible this was due to the really demanding hardware requirements of the game. It really required a top-of-the-line PC to play smoothly. The game was so resource hungry because it was the first game ever to use 3D texture-mapped synthetic actors. And this was before hardware-accelerated graphics, so BioForge had its own purpose-built software 3D renderer. The developers pioneered skeletal animation and live motion capture, which is now used in almost all 3D games with 3D characters. They really pushed the hardware as far as it could go to create amazing dynamic environments. The world couldn't be fully 3D because of the hardware limitations. So instead they modeled the world in 3D and then they pre-rendered multiple fixed camera angles to create 2D backgrounds that the 3D characters moved through. This is sometimes referred to as a 2.5D game. And on top of all that, extensive voice acting and sound effects cued by distance really immersed you in the story. So this is the first thing that most people think of when they hear reverse engineering in relation to software. You know, disassemble the executable, right? So this was my first instinct too. And this is actually a capture I made disassembling the BioForge executable. BioForge uses one of the first DOS extenders from a company called FileApp. They were arguably the inventors of DOS extenders. And I managed to track down a copy of the FileApp SDK, which conveniently had a disassembler. And that allowed me to dump out the quarter of a million lines of assembly that you can see here. But let's take a step back for a second and have a look at the files included on the game disk. So we've got a 1 megabyte, approximately bioforge.exe. We've got some English, French, and German readmes, and some key code mappings, and some very helpfully named folders. So let's take a look inside some of the folders. So the data folder contains a bunch of files with the extension .fnt. It seemed likely to me that these are game fonts. The music folder has a bunch of DLLs for different sound cards at the time, and 2 files with the extension .flx, ken.flx, which I assume is named after Ken Demarest. He was the director of BioForge, and music.flx. Looking at these 2 files, I found that they're actually binary identical. I'm not sure why they were both included on the CD. But I assume that they must contain the music for the game. The sound folder contains 3 files, also with the extension .flx, and I guess that these must contain the game sound effects and voice samples in English, French, and German. You've got the prefix letter of E samples, F samples, and G samples. The monitors and rooms folders contain a few hundred files with the extension .cam. And looking at the names of the files after playing the game, I figured that they must be the pre-rendered backgrounds or the cameras which make up the BioForge world. The script folder contains over 100 files with the extension .scp, and you can actually open up these files in a text editor, and they're quite readable. I'll show you that a little bit later. But they're obviously scripts defining the game's logic. And the show folder contains 6 files with the extension .sho, including endgame.sho and intro.sho. It seemed likely to me that these were the intro and endgame movies from BioForge. So just a tip at this point, if you don't want someone reverse engineering your own software, don't tell them what each file is by using nice, meaningful names. At least do some basic obfuscation, not just of your code, but also the names of your production artifacts. Anyway, after looking through the files, I came to some conclusions. First of all of the gameplay logic is contained in external scripts, not the executable. And the scripts are somewhat readable. And secondly, I already knew that BioForge uses a software 3D renderer, but these days we have hardware 3D rendering using OpenGL, for example. So I didn't need any of the rendering code from the exe. But obviously the executable must have the reader code for all of the different file formats. But I thought if I could work out the structure of the files, I could potentially avoid trying to decipher the 250,000 lines of assembly to find out what was relevant. Okay, so let's look at what we've got. Based simply on the folder names, file names and their extensions, I had a pretty good idea of what each file might contain. Here are the 9 main groups of files. Unfortunately, I don't have time to cover every single one in this hour. Actually, the hardest part preparing for this talk was choosing what to leave out. So you probably noticed that I skipped over a few of the directories as we browsed through. They turn out to contain the 3D media of the game. And at the risk of turning this into a maths lecture on quaternions and spherical linear interpolation, which could take an hour alone, I'm going to just focus on the first 6 formats. But it just so happens that we can recreate the entire intro and title sequence of BioForge with just the first 6 formats. So to do that, we need to reverse the structure of each format and code some readers for each of them, and then glue it all together. But before we start trying to decipher the structure of each format, there is another thing we can try. There's a nice and easy way to see if any of the file formats have known specifications by using the file command in Linux. So let's take a look. I'm going to just run the command under Windows Subsystem for Linux. So here we're just running the file command or executing the file command across all files on the BioForge CD-ROM. So it turns out that nearly all of the formats are unknown. Many of these are false positives, except for the files with the extension .sho down the bottom here. So this is telling us that these are actually FLC animations. These are effectively animated images without any sound, and they were very common in the mid-90s. You can find them on lots of magazine demo discs from the time. So in the case of the .sho files, I got lucky. I grabbed the format specification for FLC animations and I coded up a reader and a viewer, but still no sound. So just silent movies, but we'll get to that later. So 1 down, 5 to go. So let's move on to the fonts. I'm going to take you through right from the start to the finish exactly how I reversed this format. I'll spend most of the time here because the techniques I used are very similar for all of the other formats. There are a few things we already know about the fonts. As you might have noticed from the game clip earlier, BioForge uses different fonts for things like subtitles, menus, and in-game screens. And given the era of the game, it's likely that BioForge uses bitmap fonts. A bitmap font is just as it sounds. Each letter is effectively an image or an array of pixels. And the predominant character set on PCs in 1995 was extended ASCII with 256 characters. And the first 32 characters in extended ASCII are typically non-printable. So each of these pieces of information, you'll see how they came out in the wash trying to reverse this format. Okay, so let's get our hands dirty. So there are awesome modern tools like IDA Pro and Katai Struct and 010 Editor for reversing software. But I've purposely decided to go back to basics here, not only because I didn't have fancy tools back when I did this myself, but also because I think you learn more without all of the magic. So I'm just going to be using Visual Studio Code with the hex dump add-in and Windows Calculator. So I've opened up the first font file, 0.fnt, to view its contents in hex in Visual Studio Code. So the first thing that we're going to do is take a look at the minimap in Visual Studio Code. I've often see the structure of the data from the minimap or significant structure. So let's have a look at that. So if you look over here, you can actually see that it looks like there's a bit of a change in the data up here and also down a bit further. So let's jump to this first change in the data and see what address that is at. So we can see here that the data seems to change around here, which is around hex 419 or 41A. So if this is a significant point in the file, then it's likely that there's some kind of pointer or offset to this address in the header of the file. So if we jump back to the top of the file and we just start scanning from the start of the file, we can see there's nothing much here that makes sense to us. But as we get 6 bytes in, suddenly we see something that we just saw. So we saw that first address was 419 or 41A. So we've got a 41A here in little endian, so in reverse byte order. So this file must be in little endian format. So we had the 6 bytes here, which we don't know what that is yet. And then we had 41A, which is likely a 4-byte offset because it's just padded with zeros here at the start. And then if we keep scanning, we can see that there's something interesting here as well. So if you're a quick thinker and you work with hex codes a lot, you might notice that 457 in hex plus 3D, which is 61, 41A plus 3D, which is 61, equals 457 in hex. So it looks like we have an offset here followed by some sort of size and then another offset. And then this this repeats. So we have another 61 bytes, another 4-byte offset, and then another 61 bytes, another 4-byte offset. And if we keep going like this, we find that we get these 2-byte sizes and then followed by 4-byte offsets all the way down to that first change in the data structure. So this must be a header with offsets into the rest of the file. So if we jump down to that first offset again, so go to 41A, and we extract 3D bytes, so 61 bytes. So that's 61 bytes. So if we copy that to the clipboard as hex, and we'll just paste that into a new file, and I'll just make it uppercase just so it's clearer. If we analyze this data, we see that it seems to be split into 3 sections. It's a bit hard all on one line, so I'll split it up for you. So we've got something here, which is possibly a header for this piece of data. So I'm guessing, or I guessed at this point, that this file has to include the font. So if it includes characters of the fonts in ASCII order, then maybe this is the first character. So this character header seems to be followed by 4-byte or 2-byte offsets. We have these numbers decrementing by 1. But then that's followed by what is presumably the character data. But this is just all ones, which is kind of nonsense. But if we think back to the ASCII table, as I mentioned, the first 32 bytes in the extended ASCII table are typically non-printable. So if that is if it is in ASCII order in the file, then that first character is effectively null in the ASCII table. So it would make sense that it doesn't have any meaningful data. But if we pick a character in the table that has, some obvious structure, so I've picked H here because it has obvious vertical and horizontal structure. If we pull that data out, maybe we'll be able to recognize the H in the data. So let's jump back. So to find the H in the file, which is decimal 72 in the ASCII table, we need to do a quick calculation. So we had 6 bytes at the start of the file, which we didn't know what they were. And then we had 6 bytes for each character in the header. So 4-byte offset and a 2-byte size, so 6 bytes for each character. So we do 6 times 72 plus that first 6 bytes. So this gives us 1B6 in hex. So if we jump to that offset, 1B6, so this should be a 4-byte offset to the H character, which is 165 bytes in size. So if we jump to 20F7 and extract the A5 or 165 bytes, that should be the capital H. So let's do that. Jump to 20F7. And let's extract the 165 bytes. So again, I'll copy that to the clipboard as a hex string. And we'll paste that into a new file. And again, I'll just convert it to uppercase to make it clear. And the first character that we extracted wasn't a total bus. That showed us that there are 3 sections to each character. So there's some kind of header, followed by a bunch of offsets, followed by what should be the character data. And if you look at this data, you can see that these must actually be relative offsets into this character data. And it turns out that there's actually 20 offsets. And if we look in the header here, we see the number 20 in hex, which is 14. There's also a bunch of 8s all over the place. So if we just split up this data in the third section based on those relative offsets, maybe we'll be able to see something. So I've done this before, so I'll do that quickly. So you may be able to start seeing the pattern, or a pattern that we're expecting. So if you haven't noticed it, it might help if I highlight all of the hex FDs here. So if we do that, you can quickly see that there's the shape of an H here. It's a little bit jagged and skewiff. But if we look at the data a bit closer, there are some other numbers here that have some meaning. So the number of rows here, or the height of the character, as I said, is 20, or hex 14, which appears in the header. And the numbers ignoring the FDs in each row all add up to 8. So we've got 8, 8, 8. Then we've got a 2, a 4, and a 2, which is 8, and so on and so forth. So these numbers must add up to the width of the character. And if we look in the header, we can also see 8. So this header is obviously telling us the width and the height of the character. We can also see that all of the FDs are always preceded by a number, which is the count of FDs that follow. So we've got 2, and then we've got 2 FDs, and 2 and 2 FDs. And then down here we've got 8 and 8 FDs. And the number, preceding that, therefore must be the skip count. So we've got, the number of pixels following, but to make the line add up to 8, we also need to know how many pixels to skip in. So, if we follow that, we can see that this would make the H line up. It would make it more what we're expecting. So you might also notice that there's a bit of redundancy in the data here. So we already have the number of pixels following, so we didn't need to actually have 8 FDs there. We could have said there is 8 FDs rather than repeating the data. And this is called run length encoding, or RLE. I'm mentioning it now because this is going to come up in one of the other formats a little bit later. I can only guess that because the fonts were already so small, the developers never looked at optimizing their size. So that's my best guess at why they didn't use run length encoding here. So here's an overview of what we found. So we had a 6-byte font header and then an array of 6-byte character records containing the offset to and the size of each character's data, followed by all of the characters in ASCII order. And each character has those 3 sections: the character info with the character's width and height, followed by the row offsets, and then each row using that simple skip count, pixel count format. Yay! So let's get to some code. That's the end of the hex that I'm going to be showing you. So I've just got a simple demo here. So we're going to read in the font that we just saw in the hex editor, 0.fnt, and then we're just going to dump out all of the characters as a single image, bitmap image. So let's have a look at the code that actually does the reading. So this is really leaning heavily on the binary reader in .NET. So we've really just got the one function here, read font, and it's really quite simple. We just go through reading in those bytes that we found. So the first 6 bytes of the file, after I went through each character manually, I found that the first 6 bytes are actually the maximum character width and the maximum character height. So we've got 2 bytes for the width, 2 bytes for the height. And then the following 2 bytes were actually the number of characters in the file. So then you know how many offsets and sizes are going to follow in the header. And because we're going to be using OpenGL to render everything, we're going to just output the font characters in a texture atlas, which is essentially just an image. So we're just allocating space for that image here. And then we use the offset table or the records, character records, to jump to the first character. And then we just loop through each character and we follow that simple algorithm that we found to read in the pixels of each character. So first we read the first byte, which is the number of pixels to skip. And then the next byte is the number of pixels. And then we read in each pixel into the correct offset in our image or texture atlas. So let's run this demo and see how it works. So this is what the 0.fnt font looks like. And for good measure, let's run it on one of the other fonts. So this is the file 1.fnt, and you might notice or recognize that this is the font that is used for the subtitles in the clip that I showed you earlier. So we can now read in all of the fonts. Now, it's not lost on me that these are just fonts, nothing terribly exciting. But it does feel good to, crack the puzzle that maybe no one else has. So we now have readers for the silent movies, as I said, and the fonts. So let's move on to the sounds and the music. So the installation guide already told me that the music is general MIDI, but these... there are no MIDI files on the game disk, so I figured they must be stored somehow in the music.flx file. And in 1995, it was common to simply store recorded sound as raw PCM or pulse code modulation. PCM's, a common way to digitize an analog signal effectively. You sample the amplitude of the waveform at uniform intervals, and then you quantize the values within a given range. So values in PCM are typically 8 or 16-bit, and they can be signed or unsigned. And there are a range of common sampling frequencies. So this information will prove useful in reversing the format. So I'm not going to subject you to another wall of hex code because the techniques I used to decipher the music and sound files were very similar to the fonts. And as you can see, it turns out that the structure of these FLX files turned out to be very similar to the font format. So we have a header followed by records with offsets and sizes, just like the fonts. And, that points to the data within the file. So you can think of the FLX format a bit like an uncompressed zip file. And in this case, music.flx contains all of the MIDI files, and esamples.flx contains all of the raw PCM recordings for English. So let's jump straight into the code. So I've got a quick demo here for the music. So we're basically just going to read in the music.flx file using a reader similar to the font reader called a flex reader for FLX. It turns out that the MIDI stored in the music FLX file is actually extended MIDI format, which isn't commonly or as commonly used as just MIDI files. So I convert the MIDI files here, the extended MIDI files to MIDI format and output them to disk. But the interesting code is here in the Flex reader. So let's have a look at that. So again, we just lean heavily on the binary reader. And similar to the fonts, if we first read in the header, which contains a little bit more information than the fonts, but essentially what we're interested in is the offsets and sizes of each chunk or file within the FLX container. It turns out that for FLX, not only do the header records contain the offsets and sizes to the data, but it can also optionally contain a string name or label for each item. So we're reading in the offset, the size, and the optional label here. And then once we have those records, all we need to do to read an item out of an FLX file is just jump to the relevant offset and then read the byte array that is of that length. So jumping back to the music demo, we're reading out the byte array and just wrapping that in a memory stream. And then we're using the converter just to convert the byte data from extended MIDI format to MIDI format and outputting the files to disk. So let's run this. So this has dumped out all of the MIDI files from the music.flx file. So there's 98 MIDIs. Let's just play one of these. So if you've played BioForge before, you might recognize this as the menu music. So whenever you're in one of the menus. Okay, now let's have a look at the sound effects. So again, we're just using the Flex reader that we wrote for the music .flx files. And but this time, each chunk that we read out, or the byte array that we read out of the FLX file, is raw PCM data. So similarly to the extended MIDI to MIDI, we're just going to convert the raw PCM data to a WAV file and output that to disk. Now, this one was a little bit trickier. The technique I used here was essentially brute force. You might recall that I talked about the common frequencies that are used for raw PCM, and it can also be signed or unsigned data and of different sizes, but there's not really many combinations there. So I effectively just went through and tried the different combinations. So here we can see the converter. So a WAV file is already raw PCM. You just have to write the header data for what format that PCM data is. So I'll just first of all show you what one of the sound effects is like, and then I'll show you how it sounds with different combinations of those formats.
This is Marine Dropship Ronik to control.
So this is one of the voice samples. You can see that the samples.flx file contained 718 samples. All right, so let's see what that sounds like with the wrong format. So I'm going to change the frequency here. And play the same sound effect.
This is Marine Dropship Ronik to control.
So it's immediately obvious that that's not the right format. Similarly, with the sign of the data, if I change the sign of the data and run that,
This is Marine Dropship Ronik to control.
So that doesn't sound too good, obviously, but you can still hear that the data must be raw PCM, but the format is not correct. So yeah, that's effectively how I reversed the music and sound effects. So let's move on to the CAM files. So you might remember that just based on the file names, I already had a pretty good idea that the CAM files must contain the pre-rendered background images for the game. I knew that, from the BioForge installation guide, that the game uses VGA, and it has 256 colors at a resolution of 320 by 200. And I was already familiar with run length encoding, which we touched on earlier with the fonts. So after opening the CAM files in a hex editor, I found that they're actually FLX container files, which we saw with the music and sound effects, just with the extension changed to .cam. But I still had to work out the structure of each item, or the chunks of data within the FLX file. So the first thing I noticed was that the very first chunk of data, or the first item in every CAM file, was always 768 bytes. It struck me pretty much straight away that it must be a color palette, because I knew that BioForge uses 256 colors, 24-bit colors. So, 256 times 3 bytes is 768 bytes. And then using the exact same process as I used for the fonts, I broke down each item, which turned out to be layers of the image, and each layer could have one or more frames. The trickiest part was realizing that each row of a frame could either be uncompressed or compressed using run length encoding. It's probably easier to visualize this format. So here is a frame from one of the CAM files that you might recognize from the game clip earlier. This is at its native resolution of 320 by 200. So you can think of this as one of over 200 fixed cameras throughout the BioForge world. As your character moves around in 3D, the camera that gives you the best vantage point as a player is shown. It gives you the sense that you're playing through like a movie, but the camera angles can make combat difficult sometimes. I just heard everyone that's played the game laugh. So each camera can have one or more layers, and each layer can have one or more animation frames, a bit like a GIF or a GIF. So let's take a look at some code. So again, I have a demo here for the cameras. It's a little bit longer than the other demos, but effectively got a camera reader. So similarly we had the font reader and the flex reader. This time we have a camera reader, and we're opening up one of the CAM files on the game disk. So that we're then reading in all of the frames from that file, and just doing a bit of composition here to overlay the different layers and pick out one of the animations, which I'll show you shortly. And then we're going to output all of those frames with the different layers composited together into bitmap files. And then we're just going to convert that to an actual GIF, so I can show you easily what it looks like. But really all of the code again is in the reader. So let's take a look at that. So in this case, as I said, the CAM files are actually FLX files. So we're letting our Flex reader do all the heavy lifting, which underneath is using the .NET binary reader. So as I said, the first item in a CAM file is always a color palette. So we're reading that in just immediately on construction here. And then we essentially just have a read frames function, which returns an array of images extracted. So this code is all very similar to what we've seen before with the other formats. So just reading in all of the different pieces. Again, we have records with offsets and sizes. But one of the things that I wanted to point out here is just where we read in the pixel data. So as I said, this was one of the hardest parts with this format, is realizing that run length encoding can be used, and it can alternate between uncompressed and compressed. So here we're determining from one of the header bytes whether the row is using run length encoding. And if it is, then we just read 1 byte and then we just repeat it the length number of times in the output image data. And if it's not compressed, then we loop through reading a byte for every pixel. So let's jump back to the demo and run this. So this has output all of the frames of this particular cam file with the layers overlaid, and then just converted that to an actual GIF just so I could show you. So this is one you probably recognize from the end of the game clip that I showed right at the beginning. Okay, so we're almost there. We just need to, have a look at the scripts so we can glue everything together. So let's have a look at the scripts. So this is what the scripts look like as plain text, just opened up in Visual Studio Code. They're actually very readable. So this is the intro.scp script, which we need to complete the BioForge intro and title sequence. There are clearly named subroutines. There's things like if-else statements and variable assignments. You might be wondering about the question marks. So, the non-printable characters are actually just numbers representing in-game built-in functions and variables as indexes into plain text definition files. Think of it kind of like an enum. So there are also plenty of comments sprinkled throughout the 100-odd script files. They are really helpful and also very entertaining. I had to censor this one for this presentation. And I also like this one. It's referring to the operating theatre scene, which we're about to see. Playing the game when I was younger, I'd always thought that they had purposely slowed the frame rate in that scene to make it feel more dreamlike. But apparently it was slowed so that double-speed CD drives could keep up. So seeing all of these comments is a good reminder to avoid leaving your comments in your production code, particularly if you don't want to help anyone attempting to reverse engineer your software. Still within the intro.scp script, this subroutine represents one of the scenes in the intro movie. So each line is essentially triggering a sound effect or a MIDI track to play in precise synchronization with the intro.sho animation. Okay, so let's join it all together and run the intro and title sequence for BioForge. So we'll be using my work in progress engine that I call BioForged with a D. The engine's written in .NET Core and uses OpenGL with GLFW and the Fmod sound system to simplify cross-platform compatibility. So let's hit F5 and see the results. So this intro sequence shows the events after the main character has been abducted and leading up to him being operated on to become a cyborg. Let's try going full screen. Now, one interesting thing that I'd like to point out is the moon and the planet around. So not very interesting, but if you search online for video walkthroughs of BioForge, you'll see that most of them are stretched horizontally, and the planet and the moon look squashed. That's because BioForge was designed to run with a 4x3 CRT monitor at a resolution of 320 by 200. So the apparent pixels are not square. But here I'm using the correct aspect ratio, and so we get nice round planets. So the game intro is being generated on the fly by combining the content from intro.sho, the music from music.flx, and the sound effects from esamples.flx. And the music and sound effects are synchronized with the animation precisely using the intro script that we looked at. So the operating theatre scene that I talked about is coming up soon. So if you don't want to see it, please feel free to minimize or mute the stream for about 30 seconds. So this is the scene that I had always thought was a dream sequence, and the frame rate was purposely slow. But as we saw from the comment, it was slowed down so double speed CD-ROM drives could keep up. Okay, so following the intro sequence, next up we see the title screen of the game. So the background here is actually coming from a .cam file. And then we have the mouse pointer here, which is the character's hand. So this is also coming from a .cam file. And then we have these buttons, which are coming from .cam files, including the hover effect. So the hover effect is actually another frame effectively in an animation. And then we have a nice font that we wrote the reader for. And we've also got the music that we heard earlier playing in the background. So let's click a button. So that's it. If you're interested in knowing more about BioForged, please follow me on Twitter at Tim Comport, or you can see my blog at timcomport.com.